All right, let's go ahead and get started with the announcements. All right, so we've got a hand-in homework due next Thursday, November 14th. We've got online assignments due tonight at 11:59 p.m. That's the chapter 13 assignment. No class on Monday, so there's a Veterans Day going on. Question? Ooh, I'm not sure. No, according to some colleagues. Yeah, nah, there's not. I mean, it's a holiday, so. December 12th is the exam number 3 in the NULH. It's here. Yeah, it's the final. Yeah, so no more exams except for this one. It's the last one. It's the last day. Question? Yeah, so it's not cumulative, but it will really help you if you know the other stuff. All right, so I'm glad you're all here. Glad you're all high energy. That's good. My goal for today is to get through this chapter. If we could get to the end of this chapter, I think we'll be sitting pretty good. All right, so let's try to keep the talking to a minimum. That way we can continue. I think it's starting to get a little quieter in here. That's good. All right, so last time we handed out some peanut M&Ms, and more importantly, we measured their weights, and we found the sample standard deviation S of those of the net weights of those M&Ms. So we can construct a confidence interval with this. But then there's a little bit more that we need to talk about here because we've got an issue here is we know S and not sigma. So that's an issue. All right, so let's just go over the central limit theorem here. There's 3 things we know. We know y bar is approximately normal. Centered at mu. Standard deviation of sigma over square root of n. And then we can use this part to find the standard error. Instead of sigma over square root of n, we would use s over square root of n. All right. So the main thing we're going to learn today is a new distribution, so an entirely new distribution. So you'll want to be prepared for that. All right, so this is the new, this is the finding the confidence interval using a normal distribution if we happen to know sigma. So like usual, this is the standard error. No, actually, it's a standard deviation because it has sigma in it. The standard error is down a little bit lower. This is the standard deviation of y bar, and then we've got the margin of error right here. All right, but instead of using sigma, we want to use the sample standard deviation given by that formula we learned a while ago. All right, so we did that and we found S, and now this is called the standard error. And the issue here is that there is a little bit extra estimation going on here that affects our interval. So we need to work off of a different distribution. So that's what this bullet is saying right down here, is that we're accounting for the extra variation when estimating sigma with S. And the reason why we do that is so that we get confidence intervals that are actually accurate. So they reflect the percentage of intervals constructed in this manner that would contain the true mean in the right way. All right, so Gossett, he was a head brewer for Guinness, this guy. So it's kind of cool. He was the one that first came up with T distribution. Well, wrote a paper about it. So he's a head brewer of Guinness. That's the beer company. His company did not allow scientists to publish confidential data, so he used a what do you call it? An alias. He used the name student to publish this paper, so that his name wasn't on it. Anyway, so he was looking into this and he was trying to get the proper confidence intervals and the proper distribution there. And he found something called the student's T distribution right here. All right, so now we're using a standard error here instead of the standard deviation. And what we're doing here with these, the y bar minus minus mu, this reminds me of like the z scores. So just trying to understand what the distribution will look like right here. And the T distribution depends on the degrees of freedom. So how large your sample size will affect what the shape of this distribution will be. All right, and that's best seen by that little graphic on the bottom of page 213. All right, but you should look at this right here. Let's go through this, what the confidence interval for population mean using the T distribution. So now we're using T's instead of Z's. And instead of a Z star, we have a T star. And you want to specify the degrees of freedom because it changes based on what the sample size is, how many degrees of freedom there are. So if we use DF for degrees of freedom, DF just equals n minus 1. Right there. And you can see it down here as well, n minus 1. Underline there. All right, and so you may be wondering, when do I use a T distribution? Pretty much you use it when you don't know sigma. So when you have the extra estimation of the S of what sigma is, or you're trying to estimate sigma using S, you want to use the T distribution. So that's how you know when to use the T distribution instead of the Z distribution. All right, so that's important. Or else you'll just be doing the problem completely wrong because you'll be doing the wrong distribution. Yeah. So, I can write it down too. Yeah, I'll write it over here. So use t distribution when we don't know sigma. Otherwise use the z distribution. And this is only for means, of course, because remember back with the proportions, we didn't even use sigma or s or anything like that. We just used p hat, q hat, and n. All right. So I definitely try to keep this straight because it's really easy to get this mixed up with proportions. Yeah. So I would suggest trying to keep this straight. All right, let's look at the t distribution unless there's any more questions. All right, so it looks like this. So this is the family of t distributions. And when you say family, all that means is that we have a bunch of these distributions. They're all sort of like each other, like a family. But some of them are taller and some of them are have wider tails than others. And it purely depends on the degrees of freedom is what this shape depends on. So with only 2 degrees of freedom, you have a shorter mound-shaped distribution with bigger tails. But then as the degrees of freedom, or the sample size, -1, goes higher and higher and higher, you are approaching the normal distribution. So this little dotted, the dotted distribution is fairly close to the normal distribution, but it still has bigger tails. All right. So the reason why we need a little bit more area in the tails is because of that extra variation that you get from using S instead of sigma. All right, so if you say you had like a sample size 1,000 or 10,000, you could use either the t distribution or the z distribution because they look so much similar to each other. And you'll see this on here in a bit. I'll show you that. All right. Any questions? Let that sink in for a little bit. New distribution right here. So it pretty much looks the same, but it's going to give you different numbers. It's going to be better. It just works better in these cases. All right, so there's 3 properties. It's symmetric about the 0. It's mound-shaped. It's got wider tails. And then you just need to know the degrees of freedom to specify which t distribution to use. And the reason why is because if you don't know S, you don't really need, you just need to find that t star, and to find the t star you use the t distribution centered at 0, so you don't need to shift it around or anything. So that's why you only need to know the degrees of freedom right there. And then, yeah, I said 4 already. All right, so let's look at a table, a t table. And this is in your book right here. All right, so this is on ACE-65. Don't forget the dash if you're looking at this. And we've got two tails or one tail. The one we want to look at is the two tails, because that'll give us the T star. And it's really helpful if you look on the bottom here. So like for a 95% confidence level, you'd use this column, the third column. And that matches up with the two-tail probability, 0.05. So 95% is in this white region, but then 5% is in the tails. All right, and then on the left here, you'll see a DF. So that stands for degrees of freedom. And you, depending on what the degrees of freedom are is what number you pick here. So you'll notice that as you go down the column, the value gets a lot smaller and smaller and smaller, and then it converges to the Z stars, the critical values here. So 1.960 should be familiar. Same way with these other guys. So if you had something like 1,000, I mean, you're off by a little bit, but not that much. But something like 10,000, you'd be even closer to what the Z star, the critical value, would be. All right, so we want to find the critical value T star for a 90% confidence interval with 14 degrees of freedom. So we're in this column, the 90% confidence level. And we're looking for 14 degrees of freedom right there. All right, so it's this is a T star equals 1.761. All right. So you need to use the T table to find these values. The TI-84 is you're able to do something called a T inverse norm, but then the TI-83, it doesn't quite have that. So you should be able to know how to find those values using the table. With the TI-84, yeah, I could. Do you have a calculator? So let's try to find the one. So degrees of freedom of 14. So this is I'm quite sure that it's not on TI-83. So stat, we look for a oh, here we go. Second distribution, inverse T. That's what we want. And let's draw a little picture here. Second distribution. And then inverse T. All right, so we want something that has a 90% within the middle here, confidence level. So that'd be 5% here. On the left tail, 5% on the right tail. And like normal, this goes from the left. So we need to put in 95% right there. So 0.95. And then we also need to put in the degrees of freedom, so 14. You get 1.61. All right. Any questions with that? Just something to know. I mean, you could look at the table too, so. All right, so let's find the T star for 95% confidence interval with 115 degrees of freedom. So we've got 95%, 115. So it's not quite, it doesn't, there's not enough room on the table to include every little bit here. So you want to be conservative, and you want to have a wider margin of error. So you would use this value, the 1.984 right there. So that would give you let's just, we could do that to see that as well. Inverse T 0.975. Degrees of freedom is 115. You see it's a 1.9808. Oh, you can't see that. Yeah, there you go. Oh, okay. So that's because 2.5% is in the left tail, and you want the calculator only knows how to go to the left. So it includes 0.95 and 0.025, which is 0.975. So like with the picture, it looks like we got 95 here, and then 2.5% right there. And you would have to include both of those. And we go to the left. All right. Questions with that? All right, so always round down the degrees of freedom. The desired line is not in the table T. And when we did that, we got a T star of 1.984. And why? This will give you a wider confidence interval. So that just means that you're under no illusions, and you're more likely to capture that true mean if you have a wider interval. So that's the conservative choice. All right. Any questions with that? Okay, so let's go back to page 215. Go forward to 215. All right, so here we've got, for now, we can assume that it follows a normal model. And then we'll examine this assumption and other assumptions. But let's just do the computation for the confidence interval. So our sample size was n equals 24. Let's do a 95% confidence interval. And to find the net weight mu of all M&M packages. The critical value is, and we can look this up, so T star 23. So T star 23 right here is 2.069. And that's what it says right here. All right, so our y bar was, let me just write this down. If we think back, it was, we had a y bar equals 51.9 grams. And then we had an S, standard deviation, equal to 2.22 grams. All right. So now we just we just do plug and chug now. So we've got 51.9 plus or minus 2.069 times 2.22 all over the square root of 24. And then let's break out the calculator. 51.9 minus 2.069 times 2.22 divided by the square root of 24. And then we also have plus. All right. So let's write that as an interval. We've got 50.96 going to 52.84. So that's an interval. And let's have our calculator do that for us as well. The calculator knows how to do it. So second distribute. No, this one's under stat, under tests. And then we're looking for the t interval. You can use the data, like type it into a list and just have it find it for you. Or if you're given the stats like we are, so we're given, well, we found y bar and we found s, so we want to put those back in. So we would use 51.9 was x bar or y bar, same thing. S was 2.22, n was 24, and then we had a confidence level of 95% or 0.95. All right. You enter on that, and it'll give you the same thing right there. All right, so here's a question. We can do the same thing, but with a z interval. And I wonder, would it be wider or narrower than our t interval? So take a moment or two to try to think about that. Maybe take a guess. Wider or narrower? Write it on your page and see if you're right. So let's. It's really quick to do. So z interval, and we're just going to say that sigma is really 2.22, even though we've got no right to say that. Let's just assume it. Let's just try that, and then let's calculate that. And this one was narrower. So this is for t interval. And then we've got z interval, which is not going to actually give us the 95% confidence intervals, because they're too narrow. So they're going to miss it more often than you think they should. So if you ran like a simulation, this would actually be less, maybe like 85 or 80% of the time. So just for a little bit more motivation here, why even do the t distribution stuff? It's so that we actually get the right confidence intervals. Because we're right here, we're off, it doesn't seem like a lot. we're off by not that much on the lower bound, but then on the upper bound, we're off by, well, not that much either, but it'll actually mess it up for us. It'll mess it up. This difference becomes more pronounced with smaller sample sizes. So like 5 or 10 as opposed to 30 or 40. So the conclusion here is that, well, we can see that most of these are above the 49.3. Well, this entire interval is above the 49.3 net weight that was on the packaging. So we could say that this confidence interval gives us evidence that the net weight of peanut M&Ms is at least 49. So I should include this word average. Let's call it mu because it's of the population. Is at least 49.3 grams. All right. So that's one conclusion that could be had there. You can also just say that we're 95% confident that this that the mu will be within the t interval. So it'll ask the question will either ask you, does this give you evidence for having at least 49.3, or just what is the general conclusion for this confidence interval? What do you get from it? All right, so let's look at these and see which ones are good and which ones are bad. These possible interpretations of the confidence interval. All right, so we've got 95% of all M&M packages have net weights in this interval. Do you guys feel good or bad? Good. Like it. Maybe it's a little fishy. A little M&M-y. All right, so the issue here, so no, I don't like that at all. Because we're talking about one interval here, and we're not talking about the mean or anything about these M&M packages net weights. We're just talking about the individual M&M packages here. So we can even think back. We can even look back to our what was it? We recorded the weights here. Right here, just to kind of clear this up. So remember, we actually recorded these. And as you can see, you would think that like maybe one would be outside that interval. But we have 49.3 is out. This one's out, that one's out. This one's out, that one's out. So this is way more than 95% are outside that confidence interval. All right. So yeah, this first one's bad. All right, the second one. We're 95% confident that a randomly selected package will have a net weight in this interval. It's not much better, actually. All they put was this randomly selected. That's the only new thing here. And it's, I wasn't biased when I was picking these M&Ms from the store. I wasn't biased. I was just picking M&M packages. So it's like also bad. I did not weigh them in the store before I bought them to make sure I got the good ones. That would be hilarious if you saw someone do that. I want an extra 2 grams in my M&M package. Gotta hunt for it. Same price. All right. Yeah, that'd be hilarious. Okay, this one here. So we don't know whether or not this particular interval contains a true mean net weight, mu, but 95% of the time these intervals will. So that one's good. That's got everything there. Mm-hmm. Yeah, no, I'd say no. I'd say no on that. It depends on what the distribution of the population is. So maybe you have a population that's very it's got a very small standard deviation. And then maybe, but I'd still say that it's not good. And you have to think, I know this is a hypothetical question there, but if you know mu, you don't need a confidence interval at all, because that's the goal of a confidence interval, is to try to capture that mu. So, all right, let's go do the next page here. We've got 3 more pages. We can do this. 216 here. So in this class, we'll have symmetric confidence intervals. That's what this note is saying. All right, so now the assumptions and conditions. They're really close to the ones for the set your limit theorem. So yeah, this one's the same. So we need randomization. We need sample size n should be no more than 10%. It's usually not an issue. The next one is we have one of 2 things need to happen for the normal population assumption. So either the population distribution is normal, or we've got the nearly normal condition is satisfied. So there's 2 ways to satisfy this assumption. So the nearly normal distribution is exactly what it sounds like. It means that it's not extremely skewed, so the shape of the distribution is not so bad. But then you also need a little bit larger sample sizes then to help normalize that a little bit. So you could use either that or that. So either so if you can see the distribution of the population, you can just see if you can use it. If it looks normal. Or you can use the nearly normal condition, which is on the next page. Does that make sense? It's kind of a tricky question, because you can kind of get stuck always checking this nearly normal condition, but then if it is actually already normal, then you don't need to worry about it. So, all right, so for small samples, should be fairly normal. Moderate sample sizes as if it's a little less normal, it's reasonably symmetric. And then if you have about greater than 40 or so, the T method will work pretty well. So there's a little bit of a gray area here. So these aren't hard rules, but you should follow them just to make sure that you get some good confidence intervals. And then also one other thing to consider is if the data are skewed, maybe you shouldn't be using the mean. Maybe you should be trying to estimate the median instead. So in this class, we're not going to learn how to do confidence intervals with the median, but it's fairly straightforward to do that. All right, and then one other note here. So when we say that the T method will work pretty well, when we say that, what we mean is that you could pick many of these samples and your confidence interval will actually have the confidence level you wanted. So, so if we have, if it was working well, then 95% confidence intervals would have you capturing the true mean 95% of the time. But then if you've got a really skewed population, then maybe you only capture mu 85% of the time instead of 95% of the time. And that means that the T method would not be working well. And you would want larger sample sizes, so if you can. All right, so we've got another example here. So here we're raising some salmon, and then we noticed there could be some higher levels of contaminants, possibly from the food pellets they eat. So here we want to make sure that there's no more than 0.08 parts per million of Murex, which was a insecticide. And then let's suppose that we get a random sample of 30 and we test them for Murex. We want to see if we're going to hit that 0.08 ppm or not, if we'll include that within our confidence interval. So, and one other thing to note, well, here we've got the X bar from the sample. And here we've got the standard deviation from the sample. And then you should also note that it's unimodal and symmetric. So it's not skewed. That's the important part. All right, so we want to calculate a 99% confidence interval for the Murex concentration of all salmon at this farm. So we're looking for the mu, all salmon, right? Okay, so we've got 30 salmon. They're the random sample, and this is a good sample size because it would follow the nearly normal condition. Since we don't know for sure that the population was perfectly normal, already the normal shape, but it was somewhat symmetric and unimodal, which is good enough for us to work off of. So that's the nearly normal condition. Let's check. We've got this is an SRS. That's a check. And we don't have to do any of that NP greater than 10, NQ greater than 10, because we don't have any P's or Q's. No proportions here. It's all with means now. It's a little bit different. All right, so we can look up the T star from a table, t-table. Can do that. So 29 degrees of freedom, and we wanted 99% confidence level. So 29 is right here. There, 2.756. And then we use that down here. All right, so here we've got our y bar from, or x bar, same thing. We use that from up above. We plus or minus t star times the standard deviation over square root of 30, and we end up with a confidence level, a confidence interval, between 0.0705 and 0.0179. And that's the conclusion here. So what you can pull from this is that the that 0.08 is within this interval. So that gives us evidence that they are actually over that limit that they're looking for. All right. So yeah, let's go ahead and end there. I already showed you the interval, the confidence interval stuff. So.